Consider a drop of mass 1 gram falling from a height of 1 kilometer. It hits the ground with a speed of 50 meter per second. What is the potential energy at the height 1 kilometer? Then I will discuss the other question later. So, have you understood the question? If you don't understand, draw a simple diagram. You will get confidence if you draw a simple diagram. A drop, for example, a raindrop, thing like that. A raindrop, water drop, having mass 1 gram. The gram should be converted to kilogram because the mass has the unit kilogram. So the mass gram, 1 gram can be converted to kilogram by dividing by 1000. Or, yes, a gram can be converted to kilogram by dividing by 1000. Gram divided by 1000, we get kilogram. So there is a body, for example, a drop of water, raindrop. It is falling. It is falling vertically downward, falling vertically downward, and finally hit the ground. Finally hit the ground. This is the ground. Just before hitting the ground, the velocity was the velocity of the drop. I mean, the mass is given as 50 meter per second. Just before hitting the ground, the velocity, final velocity was 50 meter per second. The height is given, the height is 1 kilometer. Height 1 kilometer, kilometer can be converted to meter by multiplying with 1000. 1000 meter, understood? The height of the mass is 1000 meter above the ground. When just before hitting the ground, the velocity becomes 50 meter per second, but the initial velocity was 0, falling from the rest. For example, a raindrop falling from the cloud, understood? Initial speed will be 0, but when it touches the ground, it will have some velocity, right? So till this step you are okay. Say the understood. Till this step the diagram is clear. Ashlyn, Aaron, everyone is clear. You respond please. Rakshana.
Yes, sir.
Yes, sir.
Okay. So once you draw a diagram like this, you will get some confidence. What happens is, if you don't draw the diagram and simply read the question again and again, you will not be able to start. But if you have a diagram like this, you will get some idea. Understood? So what is our question? What is the potential energy at the height 1 kilometer? So initially the mass is at 1 kilometer above the ground. So it has a potential energy. We studied in the previous class. I don't know whether you remember or not. Do you remember the potential energy at a given height? At a given height, anybody? Potential energy is denoted by U. Do you remember that? Potential energy is denoted by U. Anybody? Please go through your notebook. Potential energy. You don't remember. If a body is at a tell me. Tell me.
MGH.
MGH. We studied in the previous class. If a body is at a certain height, it will have a potential energy. MGH. Please never forget the formula. MGH is the potential energy. M is the mass of the body, which is 1 by 1000. G we can take it as 10. G is 9.8. We can approximate it as 10. Height is 1000 meter. Hence potential energy at a given height, 1000 cancelled, 10 joules. The body at that height, the body will have the potential energy 10 joules. So not over, the first part is over. So all of you please write down till this step. If you are okay and return, raise your hand. If you have understood and written, raise your hand. Said understood. Devasri Rakshana understood. Aaron okay. Raising hand means you understood, okay, and also completed. Now I am going to discuss the second question. Find the kinetic energy just before hitting the ground. It's a simple question. The kinetic energy denoted by K. Anybody, what is the formula for finding kinetic energy?
Sir, half mv.
Yes, we studied already. Kinetic energy is given by half mv square. A moving body will have an energy, kinetic energy. Half into m, mass. Mass of the body 1/1000. V square. We have to find the kinetic energy just before hitting the ground. At that time velocity is 50. So V square will be 50 square. 50 into 50, understood. What is the value? 2 zeros cancels. I don't want to discuss all the calculations. 5, 25. What happens? Let me find the value 1 minute. Just a minute. (25 divided by 200), right? 25 divided by 200, 0.125. 0.125 joules. Only this much. A falling raindrop, think like a raindrop. You know that the raindrop will have only this much mass, understood? If the raindrop falling and reaches the ground, just before hitting the ground, it has only this much kinetic energy. The lots of energy is lost because of the friction with the air. If the raindrop falling, what happens? Definitely there will be friction with the air. The lots of energy will be lost in the form of heat energy. The friction will be there, understood? That is the third question. What is the third question? Find the energy loss due to air resistance. If there is no atmosphere, okay, no energy will be lost. But because of the air resistance, some energy will be lost in the form of heat. So the energy lost is equal to, I will tell you, the energy lost. Energy loss equal to initial total energy. Initial total energy minus final total energy. We have to consider the total energy, because a body will have two types of energy: potential energy, which is due to the position; kinetic energy, which is due to the speed. So if you want to find the energy loss, what you have to do? The initial energy minus final energy, the difference, that the initial minus final difference will be the energy loss. Initial total energy. Initial total energy means total energy, potential energy plus kinetic energy, understood? Total energy means potential plus kinetic. Final total energy means final potential energy plus final kinetic energy. Remember, total energy is potential plus kinetic. This is the right step, okay? Initial potential energy. Initially, let me call it as raindrop. Initially, the raindrop is this much height above the ground. Initial potential energy I have already found, 10 joules. Let me complete it. After that, you can ask me doubts. Initial potential energy. Initially, the raindrop is at this much height above the ground. So, initial potential energy 10 joules. Plus Initial kinetic energy. Initially the raindrop is at rest. Initially the raindrop is at rest. So no speed initially. So initial kinetic energy is 0. Initially speed is 0. Hence initial kinetic energy is 0. Final potential energy. Finally, if the body, height is 0. If the body lies on the ground, its potential energy is said to be 0. I discussed in the previous class. If the body is on the ground, earth ground, potential energy is 0. Because height is 0. If the body is on the ground, the height is 0, potential energy will be 0. So final potential energy will be 0. Ground, no potential energy. And final kinetic energy. Just before hitting the ground, final kinetic energy 0.125. You will get 10 minus 0.125. 0.125. The most of the energy is lost due to air resistance. If you subtract, you will get the energy loss will be 9.875 joules. This much of energy is lost due to the air resistance. So don't forget it. Energy loss is equal to initial total energy minus final total energy. So all of you please write down. If you have written and understood, raise your hand. If you don't understand, please ask me. Please remove your old raise hand. If you have written this, understood, raise your hand. Everyone okay? Devasri, Rakshana, Aaron, Ashlin, Said, everyone is clear. So we can go to the next problem then. We can go to the next. The important question I am discussing, the next theory topic. Okay, next is theory. Potential energy, I discussed in the previous class that there are two types of potential energy. One is potential energy due to the height. Due to height, if the body is at a particular height above the ground, it has some energy. Because if I release it, it will fall. Its energy stored will be converted to kinetic energy. So if a body, due to the height, the body will have potential energy, and there is another type of potential energy due to stretched spring. Due to stretched spring. Raj, why are you late, Raj? I will send the message.
Sir, I had another class.
Okay. Anyway, don't worry. I have recorded the class. I will send everything. Okay, but never miss the class. Okay. So all of you please listen. Potential energy of a spring. The next theory part. Look at this diagram. What is this? It is a spring. It is a spring, and at the end of the spring a mass is connected, and on a wall the spring is fixed. This left end is firmly fixed on a wall somewhere. The other end is free, meaning that I can stretch it or I can compress it. This right end is free, the other end is fixed. So a spring is connected to a mass. So all of you listen. Initially the spring is neither stretched nor compressed. Initially it is in the relaxed state. Okay. So it is said to be equilibrium position. Let us call it as equilibrium position. It is neither stretched nor compressed. The mass is standing at the equilibrium position. We can call it as equilibrium. Mean position, equilibrium position, or it is said to be mean position. Okay. Now I am going to discuss about the stretched spring. If I stretch the spring, what happens? The length of the spring will be increased. You agree with me? I stretch it towards right. The spring length of the spring will be increased. So the body, the mass m has got a deviation from the mean position. The mass has got some small deviation from the mean position. You agree with me? Small deviation, displacement. The mass has got a displacement from the mean position. It is denoted by x. Always denoted by x. X is the displacement of the body from the mean position. X is displacement, so x will have a sign. If the displacement is towards right, x will be positive. If the displacement is towards left, x will be negative. You know that a displacement is a vector quantity. So the mean position, the displacement is measured from the mean position. You can ask me doubt, but let me complete this entire diagram. Let me complete it. After that, you can ask me doubt. Okay. So a stretched spring, the body will have, the mass has got a small displacement, say x. In that situation, what you can say? In that situation, the spring pull it backward. If I stretch it and I am holding this mass. At that instant, the spring exerts a backward force towards the equilibrium position, mean position. The spring exerts a backward force like this. If I release it, because of this force, because of the spring force, let me call spring force, because of this force, the mass will tend to move backward. Understood? So there will be a force, let us call it a spring force or force exerted by the spring. Understood? Let us denote it by F. Okay, F is the force exerted by the spring. Okay, this is the situation in the case of stretched spring. Now what about compressed spring? Can I compress it? Yes. Initially the mass is in the equilibrium or mean position. If I push backward with my hand, I am pushing it backward, the body appear like this. Now it is said to be in the compressed state. The spring is said to be in the compressed state. The mass has again got a displacement, the measured from the mean position. This is x in this case. In this case, definitely x is negative because if the displacement is towards left, it is negative. Okay. The force will be there. The spring push towards right. Spring push the body towards right like this. F. So this diagram, if they are in exam, if they are asking for, explain the potential energy of the spring, then you have to draw the rough diagram. It is directly taken from NCERT text. Okay, this diagram is there. This diagram is important. So have you understood all these three diagrams? Have you understood? Said, Raj, Ashlin, Rakshana. The diagram is clear to you?
Yes, sir.
Okay. Now all of you please listen. Let me write some important points here. Let me write in sentence. X is what? X is the displacement, right? The displacement of the body or displacement of the mass of the body from the mean position. From the mean position. It is clear from the diagram, understood? And F. What is F? F is the force exerted by the spring. F is the force exerted by the spring. Okay. Experimentally, the exact derivation is not there. Experimentally, we can prove that the force exerted by the spring directly proportional to the displacement. We can do experimentally, we can prove it. The more displacement, the more force exerted by the spring. If you think about this, if you look at the diagram, you can understand. The more stretched spring, understood. The more stretched spring implies the more backward force exerted by the spring. So experimentally, we can derive it. The F is directly proportional to x. If x is increased, naturally force will be increased. if I remove the proportionality constant, what I can write, I have to write some constant in the right side. If you consider only magnitude kx, but you know that force and x are vector quantity, the sign is required here. I mean plus or minus. Look at both the diagrams, you can understand. Here x is positive. You agree with me? In this diagram, what is the sign of x? Look at this. In this diagram, x is what? Positive. You agree with me? If x is positive, displacement towards right. But f is negative, because the force towards left. If it is left side, negative. Understood? So when x is positive, f is negative. F and x has opposite sign, correct? F and displacement have opposite sign. Same thing you can see here also. Here x is negative. The displacement towards left, x is negative. But force is positive towards right. So from both the diagram, it is clear that f and x has opposite side. So I have to adjust, I have to do some modification in the formula. If I consider the sign, I have to put a negative sign in the right side. That means that if it is clear that if x is positive, f will be negative. For that purpose, I have to put a negative. So it is clear. For example, if x equal to plus 10, clearly f will have a negative sign. So for opposite, f and x has opposite side, that is why I put a negative sign in the right side. This formula you have to memorize, where k is a constant. K is a constant called spring constant. Spring constant, k depends on the nature of the spring. Nature of the spring means what kind of material is used for the construction of the spring, what is the size of the spring, what is the diameter of the spring, like that. K is a fixed number which depends on the nature of the spring. Understood? K is a constant which is called spring constant. Unit is, unit you have to understand, unit. You can ask me doubt, but let me complete the sentence. You know that k, k equal to, okay, forget about negative sign, okay, or put a negative sign, no problem. If you do the rearrangement, k equal to minus f by x, or f by minus x, anyway, k equal to f by minus x. F has the unit Newton. F has the unit Newton. X has the unit meter. Newton per meter is the unit of spring constant. In most of the question it will be given. It depends only on the nature of the spring. So if the displacement is given, we can find how much force exerted by the spring towards the mean position. Understood? This formula is very important in the chapter oscillation. In the chapter oscillation, this formula is required. Never forget it. Because of this F, the body will oscillate, left and right movement. But that kind of motion we will learn in the another chapter, oscillation. So all of you please write down, draw the diagram and write all these all these results. If you don't understand anything, if you don't understand, please ask me right now. If you are okay and written, raise your hand. Devasri, Aaron, Raj, Rakshana, Said, understood. Everyone okay? Devasri, okay. Rakshana, okay, okay. Ashlyn, clear ayo, Ashlyn. Ashlyn. കേൾക്കുന്നില്ലേ? Ashley, no response. Okay, so finished. So this one is okay. The next is okay. The next is there is a derivation. It will be asked in the exam. Okay. Next is derivation of potential energy. Next is the derivation is the potential energy of a body. Placed on a stretched or compressed spring. This derivation is required. Okay. Potential energy of a body, I mean mass m, placed on a stretched or compressed spring. The another type of potential energy we studied. I mean, if the body at a height h, that derivation I have already discussed. Now I am going to discuss another type of potential energy. We have a stretched or compressed spring. There is a vertical wall. A spring is connected. A spring is connected. I mean, a mass is connected at the other end, right end. The body has got a displacement. Let it be the equilibrium, I mean mean position. It is said to be the mean position. Mean position means at that position the body is not compressed. I mean spring is not compressed. Mean position. And it has got a displacement x. If you are not able to see, you please zoom it. X is the displacement. Okay, understood. So we have to derive the formula for finding. Let me denote. Let it be x, no problem. If the body is at a distance of x meter away from the mean position, definitely the body m will have a potential energy. You agree with me? The m will have a potential energy. Why? The reason is simple. If I release it, it will move like this. It will move towards left. So energy stored in the body. The energy is stored in the body. So any mass connected to a stretched or compressed spring will have potential energy. If I release it, that stored potential energy will be converted to kinetic energy. So I want to find the potential energy at a displacement x. All of you please listen. It may ask, two methods are mentioned in the textbook. One is integration method. Actually the integration you have not studied. You will learn in maths in 12th standard. Any of the method you can choose. Another method is graphical method. I will discuss the graphical method for finding what is that? The potential energy. Understood? So in the previous class, I think all of you, yes, everyone present in the previous class. All of you please listen. The graphical method for finding the work done. We have studied the graphical method. 1 minute. Okay, no problem. The graphical method for graphical method of finding the work I discussed. If the body is under stretched condition, there is a backward force. Understood? I will discuss in another way. Do you know integration? Let me ask you. One of the methods should be written in the exam. Do you know the integration? I think the graphical method is very difficult to understand. Do you know the integration? Please respond. Please tell me, is it taken in your school? Aaron, Devasri, Rakshana, say no. Taken? Okay, okay. Then let me discuss in another way. All of you please listen. How does this body achieve potential energy? That is my question. The body achieved the potential energy. The body initially was at mean position. the body was initially at the mean position, I applied a force towards right. Initially, where was the body? Initially, the body was here. You agree with me? Initially, the body was in the mean position. Slowly, I applied force like this. Slowly, I applied a force towards right. Slowly. And as a result, the body has got a displacement x. So I have done a work. Understood? I have done a work. Understood? I mean, slowly I am applying a force. Initially, the body was in the mean position. Slowly I am applying a force towards right. As a result, the body slowly move towards right. Hence, finally get a displacement x. So during that time I have done a work. During that time, till that time I have done a work. Whatever work I have done is stored as the potential energy. Whatever work I have done is stored as the potential energy. Okay, I hope you have understood. Okay. So my explanation take time. All of you please listen. My explanation take time. All of you please listen. If you don't understand, you can ask me. Okay. Let me use another letter. For the time being, let me use a letter A. In oscillation, you will use only A, that is why. Or you may use small letter x, no problem. Okay. So all of you please listen. So every time I have to apply a force towards right. Understood? Suppose it is at a distance x. On the way, the body is at a distance of x meter from the mean position. On the way, I will repeat, don't worry. I will repeat definitely. On the way, the body has covered a displacement x. At that instant, there is a backward force, which is the spring force. There is a backward force F. I have to apply a equal amount of force towards right. Then only the body will move towards right. On the way, the body has got a displacement x. On the way, the body has got a displacement x. At that instant, there is a backward force F. I have to apply slightly more than that F. I have to apply slightly more than that F. Then only the body will slowly move towards right. The force towards left is minus kx, right? The force towards left side is minus kx. So the force towards right will be plus kx. Sorry. Devasri Rakshana, listen, don't worry, I will repeat. Okay, I will repeat. So the force towards left is minus kx, spring force. So I have to apply a slightly more than that F or equal to that F. So the force should be kx. Kx. So under this kx, the body is moving towards right. Can I say like that? Under this force kx, the body is moving like that, moving towards right. So let me explain the graphical method I am discussing. Under the force plus kx, the body is slowly moving towards right. Let me draw the displacement force graph I discussed in the previous class. Let me draw displacement force graph. F equal to kx will have a graph like this. F equal to kx. F equal to kx has a graph like this. It will be a straight line. I mean, you studied in the lower classes. If the power of x is 1, it will be a straight line. F equal to 2x, f equal to 3x will be a straight line like this. And f equal to kx. I have to do the work done from 0 to a. I have to find the work done by this force F. I have to do the work done by this force from 0 to a. From 0 to a. From 0 to a, how much work I have done? Initially the displacement was 0. All of you please listen. After that I will repeat. Initially the displacement was 0. Finally the displacement is A. 0 to A, I am applying a force Kx towards right. Hence the body is slowly moving towards right. F equal to Kx is a variable force. As the position changes, the force changes. So I have drawn the graph of force versus displacement. Force versus displacement. F equal to Kx will be a straight line like this. I have to find how much work I have done from 0 to A. From 0 to A, how much work I have done. In the previous class, we studied that the work done by a force, the work done by a force can be found by area under the force displacement graph. The work done by a force F equal to Kx. Because of this force, the body is moving towards right. The work done by a force by graphical method we studied in the previous class, that we have a force displacement graph. The area under the line, under the graph, represents the work done. You please listen, let me complete the explanation. After that you can ask me doubt. Also I have recorded the classes also. So work done is equal to, from 0 to A, how much work I have done. It is area under force displacement graph. Area under force displacement graph. You know that it is a triangle. You know that it is a triangle. Triangle we have studied in the lower class, half into base into height. The area of the triangle is half into base into height. Base. Base is A, capital A. Understood? Base is capital A. Height. Height is force is Kx, right? The force is given by the formula Kx. When x equal to A, what is the force? When x equal to A, force will be K into A. Formula is Kx, right? Formula is Kx. So this height should be Ka. Force is the height. F equal to Kx. When x equal to A. When x equal to A, what is the force? When x equal to A, the force will be Ka. So height is Ka. Height is Ka. Multiplication gives half into Ka square. Half into Ka square. So what is my conclusion? So in order to move the body for a meter, in order to move the body a meter towards right, I have done this much work. I have done this much effort. This much work is stored as the potential energy at that position. Whatever work I do, it is stored as the potential energy. So my conclusion, let me write my conclusion. My conclusion is simple. We have a stretched spring. We have a stretched spring. This is the mean position. This is the mean position or equilibrium position. If this displacement is A, the displacement is A, then potential energy, the body will have a potential energy. Understood? If I release it, it will move backwards. So in that situation, a meter away from the mean position, then the potential energy of the body will be half Ka square. It's a very important formula in the chapter oscillation also. This derivation is important. Two methods are mentioned. One is integration method. Since you have not studied integration method, let me discuss this method, area method. So all of you please write down, draw the diagram neatly. If you don't understand any step, please ask me. Okay. Remember, I have recorded the classes also. Okay. Ashlyn response വേണം കേട്ടോ. Ashley. You can ask me doubt, don't worry, okay? Devasri, you can ask me doubts. Any step you can ask. Rakshana. Okay, you please write down everything. Devasri finished. Rakshana completed. Aaron, Snehal. Raj, your name is Snehal, right? Devasri understood. Rakshana Said understood. Ashlin, you are not responding. Ashlin. So everyone finished. This derivation is important. Remember the same theory is required in the chapter oscillation. Okay. So potential energy will be there for a stretched spring. The total energy of a spring. This is the next one. Just understand the formula. Just understand it. The total energy of a spring. All of you please listen. We have a stretched spring. Let it be the mean position. Look at this diagram. This is the mean position. What is this? This is the mean position. Actually, the body is released from some distance away from the mean position. Let me draw the diagram again. I mean, initially the mass was at some distance away from mean position. Say maybe here. It is moving, okay? And this is the temporary position. This is continuously moving backward. Understood? This is the temporary position of the body. Initially, it was under stretched condition. M is released. M is released. This is the temporary position. Okay. Suppose initially the mass capital letter M was at a distance of A, capital letter A meter away from the mean position. And this is the temporary position. Say let it be X. Give some name X. It's a temporary position. Remember, if the body, all of you please listen. In this situation, the body is moving. You agree with me? The body M is moving towards left with the velocity V. So at this position, at this temporary position, what is the total energy? That is my objective. Let us give some name. 1 minute. O. This position is P. This position is Q. Give me some name. Okay, give me some name. P is the temporary position. Temporary. Q is the maximum stretched state. Q is the maximum stretched state. Stretched position. O, you know, mean position. Okay. Q, let me give some name. Okay. This is the maximum stretched position, which is at a distance of A meter. If I release it, it will be moving backward. There is a temporary position. It will not stand here, again move. Let it be P, temporary position. The total energy at P, that is what I am going to discuss. Total energy at P, I am going to discuss. Total energy at P. What is the total energy at Q? Anybody? What is the total energy at Q? Can you tell me? What is the total energy at Q? At Q, it is the maximum stretched state. If I release it, its initial velocity will be 0. You agree with me? Initially, I am holding this maximum stretched state. If I release it, initial velocity will be 0. Initially, the velocity will be 0. No kinetic energy at the maximum stretched state. No kinetic energy in the beginning, but it has a potential energy that I derived it. Total energy at Q is half into Ka square. At Q, at the maximum stretched state, if I release the body's velocity will be 0 initially. So no kinetic energy initially, but still it has a potential energy half Ka square. What is the total energy at the temporary state P? At temporary state P, the body still has potential energy because it is at a distance of x meter away from the mean position. At Q, the body still has a potential energy half Kx square. Half Kx square plus. It has the kinetic energy also, V. The kinetic energy half mv square. Just understand that it will not be asked as a numerical question, I think so. It will be asked as a theory question. If no frictional loss, total energy at Q will be equal to, just understand that, total energy at P. Total energy remains the same. Energy is conserved during the motion. During the motion, just like a falling body, the energy is conserved. Total energy is conserved in the case of a frictionless spring. In the case of a frictionless spring, total energy is conserved. Conserved means at the extreme position it will have a total energy. Intermediate position it will have a total energy. Whichever place you select, everywhere the total energy remains the same if there is no friction in the spring. So the total energy is given by the potential energy plus kinetic energy. It will be conserved. Okay, there is a numerical problem based on this. Yes, it is there in textbook. So all of you please write down. If you don't understand, you please ask. Total energy is conserved. At the extreme position, the body has only potential energy. Okay. At the intermediate position, the body has both potential and kinetic, but their sum will be fixed. Okay. Please write down if you have written and understood. Raise your hand. Aaron Devasri Rakshana understood. Snehal okay. ആഷ്ലിൻ കുറേ നേരം റെസ്പോൺസില്ല, ഞാൻ വിളിച്ചുകൊണ്ടിരിക്കുകയാണ് പേര്. ആഷ്ലിൻ കേൾക്കുന്നുണ്ടായിരുന്നോ? റൈസ് ഹാൻഡ് മാറ്റാം. ഓക്കെ, യു പ്ലീസ് റിമൂവ് യുവർ റൈസ് ഹാൻഡ്. I think let me discuss one question. It is taken from textbook example 5.8. After this, I think okay, I can start power collisions. Okay. So all of you please listen. In 2 class, I think this chapter will be over. All of you please look at this question taken from a textbook example. It's a good question. It's a very good question. A car of mass 1000 kg moving with a speed 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant. Thus, what is the maximum compression on the spring? Let us draw a rough diagram. If you don't draw the diagram and simply read it, you cannot start the question. Let us draw a rough diagram. What is this? Let us consider a vertical wall is there, a huge spring, okay, about the car. Okay, we have a very large spring. A large spring is there, and a car is moving, approaching towards the spring. Understood? A car going to hit. All of you please listen. Please ask me if you don't understand. A car is approaching the spring. The spring is not a smaller one. It's a very large spring. Okay, nearly the size of the car. Think like that. A car is approaching the spring, and the speed of the car is what? V equal to. The speed of the car is 18 km per hour. You know that the kilometer per hour. You know that kilometer per hour can be converted to meter per second. Anybody? How will you convert kilometer per hour to meter per second? Anybody?
5 by 18.
Ah, yes. 18 into 5 by 18. Don't forget it. Kilometer per hour should be converted to meter per second. Don't forget. The velocity of the car is 5 meter per second. The car hit the spring at a speed of 5 meter per second. What do you expect after that? What do you expect after that? I will tell you. The car is again moving, but the speed will be gradually decreasing. Because of, this compresses the spring. Understood? The car compresses the spring. As a result, the speed of the car gradually decreases, and it will compress, up to maximum compression. What is the maximum compression of the spring? That is a question. This is the mean position. This is the mean position. And this is the maximum compression on the spring. Understood? Let me call it as O. Let me call some, oh, you can give some name. Okay, no problem. Tell me some name. P, okay. P is the maximum compression, okay. O is the mean position or equilibrium state. Neither compressed nor stretched, relaxed state. If the car hit the spring, it compresses the spring, and the car is again moving towards left, and gradually car stop. Gradually car stop at P. Understood? The car stop at P. At that point P, we said that the maximum compression on the spring. Understood? After that, there is no more compression on the spring. So the maximum compression is our question. So O is the mean position, right? Mean position. And this displacement, let us denote some letter. From the mean position, there is some displacement x that I want to find out. The x is our question. What is the maximum compression, which is measured from the mean position? So x is our question. Let me complete this question. After that, you can leave. So till this step, you are understood. You are okay. X is our question. You agree with me?
Yes.
Here the velocity is 0. You know that the velocity will be 0 at P. The car stopped there. At that instant, what is x? So the energy conservation principle will help us to find out. The energy conservation principle. Total energy at O equal to total energy at P. You agree with me? We are assuming it as a frictionless spring. Total energy at O will be equal to total energy at P. Total energy at O. Here, what happens? The car is suppose car is in contact with the spring. Okay, let us think like that. The car is in contact with the spring, just like a mass connected to a spring. The car is in contact with the spring. It is just like a mass connected to a spring. The mass is in the equilibrium state, mean position. In the mean position, okay. So, but here the kinetic energy is there at O, because car is moving fast. Car is moving fast. So the car will have a kinetic energy at O. Car will have a kinetic energy at O. The car is moving, right? So kinetic energy at O will be half mv square. Potential energy is not there because car is in the equilibrium state, mean position. If the body is in the mean position, no potential energy. Understood? We studied that if the body is in the mean position, no potential energy. For a potential energy, there should be some displacement from the mean position. If the body is in the mean position, no potential energy. If there is some displacement from the mean position, potential energy. So car is in the mean position, no potential energy, but car has some velocity, so the car has kinetic energy at O, but no potential energy. Car is in the equilibrium, mean position, and at P, the kinetic energy of the car is 0. At P, the car is not moving. Spring is not moving. The kinetic energy of the car is 0. But car has got a displacement from the mean position. If the car is at P, the car is x meter away from the mean position. Hence, the car will have potential energy. Potential energy has the formula half kx square. We studied already. I have derived it. Potential energy, I have already derived it. Half ka square, where a is the displacement from the mean position. So what I am saying is, if the car is at x meter away from the mean position, the car spring system will have a potential energy half kx square. I derived that formula. So all of you please write down. Let me complete this problem. After that you can ask me doubt. All of you clear till this step? All of you clear? Rakshana,
Yes, sir.
Devasri, Ashlin, Said. Okay. I use the energy conservation principle. Okay. So let me write again. Half mv square is equal to half kx square. Is that correct? Half mv square equal to half kx square. Half cancels. X is our question. K can be taken to left hand side. mv square by k. Or x equal to square root of mv square by k. V square can be taken outside because square root of v square is v. Square root of v square is v. V into root of m by k. You can substitute the value. V is 5. M is the mass of the car, which is 1000 or 10 raised to 3. 1000 or 10 raised to 3. K is the spring constant, 5.25 into 10 raised to 3. Unit is okay, perfect. It is meter. Root 1 by 5.25 will be given in the question because for CBSE the calculator is not allowed. So let me avoid the calculation. Whatever information is required, it will be given. Root 1 by 5.25 if it is required, it will be given in the question. So I don't want to discuss the calculation. Okay, Let me write the final answer. Okay, 0.95 meter is the answer. No need to convert to centimeter, or approximately 1 meter. Okay, approximately 1 meter compression will be there. So all of you please write down. If you don't understand any step, please ask me.